Okay, in this video we're going to talk about the degree and how the degree will affect the shape of a graph. So we've already talked about parabolas, graphs that are quadratic equations or quadratic functions. F of x is equal to ax squared plus bx plus c, where the biggest power of x is x squared, so the degree is 2. Now I have two examples on the piece of paper that have x to the third and x to the fourth, so degree being 3 and degree being 4. And you'll notice that the x to the fourth looks most similar to what we've seen before, the parabola shape. It's a little bit steeper, a little bit shrink down, but it is generally the same shape, whereas x cubed is doing something pretty different. Instead of going up and to the right and up and to the left, it's going up in one direction and down in the other direction. And this is all because of the degree, because when we take a negative number to an odd power, what we're going to have is negative answers. If we have a negative number to an even power, we're going to get positive answers. So the exponent being even or odd is going to tell us whether the shape is going to look like x squared, more or less, or whether the shape is going to look like x cubed, more or less. So I can tell you right away that x to the fifth is going to look more or less like x cubed. X to the sixth is going to look more or less like x to the fourth, because odd powers are going to look like, even powers are going to look like. This is something that we call an odd function or an even function. Okay, let's look at another example, more complicated example. Okay, so 5x is 7 minus 4x is 6 plus 3x squared minus 6x plus 8. And what I'm going to tell you is it turns out the degree, which is 7, and the term connected to the degree are going to have the biggest impact on what the outside edges of the graph are going to look like. So even though these are going to do something to the shape of the graph, it turns out this guy right here is going to tell us, for the most part, what the outside edges of the graph are going to look like. And it's based on two things. First of all, is the number up front positive or negative? Because like we saw with parabolas, if we have a negative number in front of our biggest power of x, then the parabola will be upside down. So if that had been a negative 5, then whatever the shape is would probably end up upside down. And then the exponent on x, the biggest exponent on x, is going to tell us, is the shape generally going to be shaped like an x cubed or shaped like an x to the fourth or an x squared. So this has an odd exponent and it has a positive number out front. And so those two pieces of information put together should tell us what the shape should look like. So I'm going to come back to this example in just a second, but we're going to break it into 4 cases. So if we have a function that's a number times an x to the n, and maybe there's some plus other junk, but also just if it's f of x is ax to the n, then the only two things we have to look at is the number a positive or negative, is the number n even or odd. So if a is positive and n is even, then we should look more or less like an even power of x, so like x squared and x to the fourth, and a positive coefficient means you're upside right, you're not upside down. So the shape would look more or less like this. If you had a was positive and n was odd, then you're going to look more or less like an x cubed. If your a was if a was negative and n was even, then you're going to look like an upside down x squared. And if a is negative and n is odd, you're going to look like an upside down x cubed. So this picture upside down. Okay, so we have 4 cases based on the number up front being even or odd, and the exponent being, the number up front being positive or negative, the exponent being even or odd. And so this example we have on the page ahead of us has a is 5, which is positive. So it's one of these 2 cases on the left. And the exponent, 7, is odd, so it's actually going to be this shape. And again, this is telling us what happens on the outside edges. So I'm not sure that the middle is going to look like this. The middle could look much more complicated. It could look like lots of wobbles, but I know the outside edges are going to go up and right, down and left. Same thing for each of these other cases. We're not really sure about the middle. We just know that the outside edges or the end behavior is going to be this shape determined by A and N. So this is how we determine the end behavior. Okay, so let's do another example with that. Hold this up a little bit. Okay, so next example, g of x is equal to minus 6x to the third plus 2x squared minus 1000x. Okay, so if I'm trying to determine the end behavior, I just look at the biggest power of x, which is this one. N is 3, which is odd. A is negative 6, which is negative. And those two things put together, looking at our previous cases, A is negative, N is odd, means it's this upside down x cubed shape. And again, I'm not really sure what happens in the middle of the graph. I just know that eventually it's going to be heading up and to the left and down and to the right. Okay, one other thing I can say, I'm not sure what exactly the shape is going to look like in here. So maybe it's just something nice and simple like an x cubed shape, but maybe it's doing something more complicated, like it's going up and down, or maybe it has a lot of wobbles. I've made this graph very hard to read, but my point is that we only know the outside edges. We don't know what exactly is happening in the middle. If it has a bunch of wobbles, only a couple of wobbles, it doesn't wobble at all. And when I'm saying wobbles, I'm really talking about, does it switch from going down to going up? And there's a special name for that. It's called an extreme value or a turning point. So extreme values or turning points are points where the graph changes from going up to going down. Okay, so as an example, this graph is changing directions at two places, so it has two turning points. This graph is changing directions at three different places, so it has three turning points. And it turns out there's a rule that says the number of turning points is smaller than the degree. And so I can use that to look at these three examples in a little bit more detail. So 2 turning points, that's smaller than the degree, so that means the degree is bigger than 2. And from the outside edges of the graph, this is looking like an upside down x cubed graph. And so we know it's got to be minus some number times an x to the odd power. And we know that that odd power has to be bigger than 2. So maybe it's a negative 4x cubed. Maybe it's a negative x to the 7th. This graph has 3 turning points, and so we know turning points is 3. That has to be smaller than degree, so degree has to be bigger than 3. So maybe the degree is 4, maybe it's 6. We do know that it's got to be going up on both edges, so that's a shape that is corresponding to an even exponent. This graph, if we look at our 3 options, let's see, I'm not sure if all these are really realistic because our degree is 3. and the number of turning points should be smaller than the degree, so the number of turning points has to be smaller than 3, and so this last one that I drew, I can definitely rule that one out. That has 3 turning points. That's too many turning points to be an x cubed graph. Both of the first two are still viable possibilities though.